A lot about what it is to be human is understanding who we are and where we came from, whether that's genetically, geographically, or otherwise. But what if we zoomed out and approached it from a galaxy level? What could we learn about who we are, what we understand about the universe, and what humans are capable of achieving? Sabine Bellstedt is an astronomer working on the epidemiology of space and on large-scale projects with international teams, not only to understand the universe, but how we understand the universe. Join us as we speak with Sabine about her journey to astrophysics, space epidemiology, and the impact of astronomical innovation. I'm Michelle Ong, and this is Steam Powered. Good morning, Sabina. Thank you so much for joining me on Steam Powered. I'm really looking forward to talking about your journey through astronomy and all the very cool things that you do.
Oh, wonderful. Well, thank you for having me.
Absolutely amazing. So we shall get straight into it and talk about how you got into this space, because you did a physics degree, but you managed to work in astronomy into it. So how did that work?
Yeah, it's interesting because a lot of astronomers tell the story about how they were fascinated by the night sky and they always wanted to do astronomy. And I think, yes, I was always fascinated by the night sky, but that was never my end game. And I wanted to be many things, but it really was just the love of the natural sciences in general. And physics is the most fundamental thereof, which is why I did that physics degree. I loved it. I was so excited at the prospect that I looked at the start of university about quantum mechanics and electrodynamics and classical mechanics. There was lots of mechanics involved, actually. And I actually had an honours project at the very end, so a final year research project lined up in the realm of condensed matter physics. And at the very last minute, I thought, you know what? I never got that taste for astronomy. And there was this spectacularly beautiful science out there that I never really got to experience. And so I did. I contacted the lecturer who was most involved in space that I could find. And I said, is there even an opportunity for me to do this? And she wonderfully got me in touch with, at the time, what was the the Australian Astronomical Observatory, which was a government-run organisation in Sydney, who had a lot of scientists that didn't really have access to many students because they weren't an educational institute. And I did a tour of the building and I found an incredible person with whom I could do a research project, and that was it. I was hooked. Here I am.
That is so cool. So, it kind of makes it hard because I can say, where did you see yourself in a career in astronomy? But you really didn't until close to the end.
And it's funny, I recently moved houses, and that's always a fantastic thing because you find all kinds of things that you've forgotten you owned. And I found a whole box of magnets that a group of friends and I had printed, mostly as a joke because there was some company that was selling free magnets and we could all personalize some things. And this was in the first year of university, and I printed off these very ambitious magnets saying, Sabine Bellstedt, astrophysicist. And I found these magnets and I thought, I could actually use these now. Who would have thought it?
That's incredible. So because you were into physics and all the engineering sort of things, and then you came to the astronomy part sort of late-ish in your academic kind of journey, what made you choose to put astrophysicist on your magnet?
I think it was because astrophysicists have this very prominent view with the public. If you think of the physicist, you think of probably many things.
They're the fancy ones.
Exactly. And they're the ones that get a lot of screen time because we have pretty pictures of space, and we've got the Carl Sagans and the Neil deGrasse Tysons and all these people that are famous that are astrophysicists. And I remember at the time thinking, oh, that must be the, to use a, crude phrase, the sexiest science. I don't know. So the seed must have been there, but I think most of my brain was thinking, no, be sensible. Broad physics. There's so much that you don't know. And it couldn't quiet that back of the brain that just thought that's where it is.
That's amazing. Like, it was just quietly in your subconscious.
It really was. Yeah.
That's so cool. So when you actually did start exploring astronomy academically and in research, what were your thoughts and where you were going to take it?
I think I had always hoped to stay in the realm of academia and research. I was always a curious child. I come from a family that has quite a few scientists in it, actually. And so that sort of pursuing just of knowledge and of research was something that was encouraged. And I think my parents joked that I would get a PhD when I was in primary school. I don't know if that came to fruition because of it.
They could see it.
Yeah, they really could. And so I'd always hoped that I could do something exciting in the realm of research. Was I prepared to not do that if it didn't work out? Absolutely. I think after my degree, I looked up a whole range of careers that I could have with the Australian Intelligence Agency because I knew this was something that...
Also sexy.
Well, maybe. Most of it was report writing, though. And it turns out I like chatting too much. So I quickly realized that wasn't the career for me. Yeah, so I always knew that there were many different options, but it was that case of just strive for the thing that you're most curious and interested in and keep an eye for other opportunities as I go. And that was always my plan.
Yeah, that's an excellent plan. Like, keeping the doors open, but, you're just letting that curiosity lead you where you want to go.
Exactly right.
That's amazing. Okay, so when we first met, you mentioned that what you were working on was the epidemiology of space. And I love that. I love that turn of phrase. It's so cool. But what does that actually mean?
It means that we're now in the regime of not just being interested in how does the heart work? How does this particular disease manifest in one particular person? What are the typical hair colors in a small group of people? See, if I liken the analogy to medicine, there are so many things that we learn in detail from a single person. But I think in the post-COVID world, we've all realized that actually learning things in detail in a single person doesn't give you enough overview of what medicine is. You need to have a really good understanding of something as an epidemiologist. How did COVID react, not just in a small group of people, but in people with different living conditions, different ages, different sexes, different ethnic backgrounds, a really cohesive overview of humanity as a whole. And that gives you a detailed view of whatever it is you're studying.
Because we're complex systems.
Completely. And that's exactly the reason why this analogy, I think, works so well, is because it's dealing with the analysis of complex systems. And in space, in physics in general, a lot of the phenomena we're studying are complex systems. And for me, that is galaxies. So I'm an extra-galactic observational astronomer, which means I look at things, that's the observational bit, but the key for me is the extra-galactic, and it's specifically galaxies, and there are many of them. How did they get to be the way they are? Now we can study individual galaxies of images in great detail, and we do. There are good reasons for that. But to understand why it is that we have, 7 orders of magnitude in size that we cover, these things have been evolving for 14 billion years, and we get anything from brightly star-forming systems to massive dead elliptical galaxies. And all of our models that try to replicate that in simulations are failing in at least one way. We've not come up with a single one that just works, right? So there are complex things going on here that we just don't understand yet. And so my small contribution to this problem is to say, well, let's study these galaxies at a statistical level. Let's try to describe every element of how they do whatever it is we're studying, because only when we have that statistical picture can we see how that mechanism, kind of like a disease in a human, propagates through the population.
Yeah. You see, when you say that, all I'm seeing is mountains and mountains and mountains of data. And how do you decide which are the things which are relevant to be able to kind of go, we need to eliminate or include, or this has more importance than this other thing, to figure out what it is that makes those models fail or succeed?
It's a really great question that the fact that we haven't answered it means that we don't know the answer to that as well as we maybe should. As far as the data that we collect for galaxies, we do the most obvious things first. How big is it? How bright is it? If we have the capacity to do more, we might, measure its color. That's a pretty fundamental one too. We do that a lot. Then we might get into structure. But first, you first try to create a model that creates the replication of the simplest property. That's often easy to get. Then you say, okay, well, we've got a bit of extra capacity now. Let's give it an extra property and try to make that work. And a lot of the time you get down 3 or 4 layers and you go, oh, now it's broken. But you can't fix it here. You've kind of got to go backwards and say, well, there's a different way of getting to the answer at the top. So let's try again. And you keep going through these levels. So as we learn more, we solve exactly this problem. We try to recapture more and more of the properties of these sources. And eventually, hopefully, we get to the point that we're more confident that we know what's going on.
Well, that's the hope. I mean, so because all of this stuff, like, I guess for a lot of people, the scale of the kind of work that you do with the size of the groups and teams that you work with, especially because this is the kind of large scale project that you need to pull in so many skill sets, so many countries, so many budgets to be able to make it all work. But why is it so important to be able to pull all these teams together aside from the obvious reasons for you just get more people?
Definitely more people is critical. I have seen small groups of people do incredible work with large infrastructure, but there are so many moving parts. Let's say, for example, one that Australia is very involved with is the Square Kilometre Array. That is a massive endeavor. That is, bigger than €1 billion project. Aside from the data analysis, right, there will be thousands of people involved in the data analysis in the decades to come. The actual sheer process of building an instrument of that scale, it involves hundreds of thousands of antennae in Australia and hundreds of massive dishes in South Africa. Already you've got a physical scale problem because you need these things to be large. And so that by default initiates lots of people and different levels of expertise in building and different levels of management, oversight, and contributors for funding. And we haven't even started doing astrophysics yet. We're just building an instrument. So the more you can lock into these big infrastructure projects, the more you gain access to new technology, new ways of thinking, and new ways of bringing together different disciplines to produce something that's never happened before.
Yeah. It's full multi-disc. It's great.
It's wonderful. It really, really is.
Yeah. And you also mentioned about access to all these technologies and developments, because one of the very cool things about these very large projects is because you are working at scales that most industries don't necessarily need. You're having to access all these technologies and all these innovations that haven't even been invented yet in some cases, and having to build all these other things that ripple down into the other industries that create all these other cool things. Like one of the funny things that came up with Catherine Bennell-Pegg talking about how the battery powered drill was actually a space thing just because they needed not to have cords, and so they developed the battery pack for power tools, and now everyone's got them and they're super accessible and pretty affordable. And that's how we get a bunch of cool tech from all of the stuff that's done on these massive big scale projects.
It's true. And I mean, I think people working on this cutting edge of projects are used or comfortable with, rather, is probably a better way of saying it, a high level of failure, because we know that this is experimental and we know that, well, realistically, you put a lot of effort into producing something that will probably never be replicated. Because why would we build an incredible telescope and then just build a second one? If we're going to put effort to a second one, you build the next bigger and greater thing. So everything's always on the cutting edge. I was at a meeting last week that was all about combining the SKA with the European Southern Observatory, which is astronomy on a very different level. And this organization in Europe is currently building the European Extremely Large Telescope. We all know how astronomers love to, have very creative names for their sources. But this is a mind-blowing facility in that it is a telescope with a 40-meter wide mirror. This is an incredible amount of glass. But the point made by the person who was presenting the current status on this project was that one of the innovations to come out of this telescope building is that when you have such an enormous amount of glass in the many telescopes we have around the world, that glass needs to be incredibly stable in temperature changes. It's not allowed to expand or shrink.
It will crack.
Well, not only will it crack, but it will have like nanometer fluctuations, because we can't afford for the clarity of our images. And so there have been enormous strides made in even just specific ceramic materials that you can use to coat instead of just normal glasses. And what I didn't know until just last week is that it's this sort of ceramic innovation that's responsible for all the cooking tops and induction cooking top technology, because that also needs to be very stable under pressure and temperature changes. So it's exactly what you're saying. It's these big picture problems that we need to come up with creative ways of solving. And then we realize, oh, wait, there are many other things we can do with that.
That's so cool. I love that, because who would have thought that a telescope could turn into induction cooktop?
I didn't, and I'm an astronomer, so it just goes to show.
I know, and it's all these really fascinating cross-discipline, out-of-the-box applications for things that you're not going to know what's going to exist until you give it a shot. And you never
Absolutely.
know what innovation you have. Someone else will go, oh, hey, I've been looking for something like this for a bit.
It's incredible. And it's exciting.
It's so exciting because you don't know what's going to come next. It's all very exploratory and very curiosity driven.
And I think that's incredibly valuable, not just for the industry applications and the technological benefits that it gets, but I think it's just nurturing for the soul. If we just know that we have new things out there to learn about, and we have the skill set to riddle out answers about our universe and the world we live in.
Yes. And I mean, if you're getting philosophical, it's pretty much, why humans exist, right? Like, people are people because they always want to know and they want to find out and they want to break things. So, we're good at this. So, as part of the work that you do, you're working with WAVES, which is the Wide Area Vista Extra-Galactic Survey, and also Gamma. All these acronyms, they really do love them, don't they?
We really do.
Galaxy and Mass Assembly Survey. So you've briefly touched on this, but what sort of things can we learn from these surveys of galaxies in the kind of scale that you're working with?
These are incredibly rich data sets where, depending on the kind of astronomer you ask, you will probably get a different answer because the applications for knowledge from these are so huge. I mentioned that I like galaxies themselves. So for me, it's about having the broadest statistical sample of galaxies. So Gamma, that you mentioned, is a precursor, not a precursor, it's a spectacular survey in its own right, and it's been in existence for over a decade now. And it's produced hundreds of scientific publications, and there's a lot that we've learned about the statistical evolution of galaxies and everything else. WAVES is a planned survey. It'll be starting in about a year's time. We're very, very excited, but it will expand the sample. So we're looking at a much greater region of the sky, and we're looking much deeper. Depth is a common term that we use in astronomy. Effectively, that just means it's like if you look at the night sky and you let your eyes acclimatize. So when you first go out into the dark sky, you see maybe a couple of stars. You probably only catch the planets because they're quite bright. You obviously catch the moon. Those are the brightest things. As you let your eye acclimatize, you capture more and more of the fainter sources. And then you go a little bit deeper. Is that how we call it? If you then use a camera, you're able to go even deeper. If you use a bigger telescope, you go even deeper. And the fainter things are either things that are farther away, so out into the distant universe, or they're just things that are smaller, so like small galaxies. Anyway, so that's depth. And so this particular survey goes out wide an area, so more samples and greater in depth, so you catch the small stuff. So that gives us the statistics for galaxy evolution itself. Wonderful. But also, if you start mapping in 3D space exactly where you find every galaxy, then you start using galaxies as a tracer. And what we mean by that is galaxies form sort of the bright backbone for what is actually a really big, spongy-like universe. And it's filled mostly with dark matter. We can't see dark matter, but if we can see enough of the galaxies, we can map out where the dark matter would be.
Like the negative space.
It's exactly like that. And there's a myriad of other exciting science that you might do that can only be done if you have a map of the universe. For example, and this is just a couple of really exciting things. If you look at quasars, so quasars are effectively feeding black holes that are phenomenally bright. If you look at quasars in a very distant universe, then the light that reaches us from them has had to move through all of the stuff that we can't see in between. And as it moves, it absorbs some of the gas, or the light absorbs some of the gas. And it means that the signal that we receive has got all of these little absorption lines in them. And those are indicators of what's in between. Now, that's a flourishing field of research that's fascinating. But to correlate that with what's happening in between is really hard unless you have mapped out the universe in between. And all of a sudden you can say, right, in massive clusters, this happens to the gas. In small groups, this happens to the gas. In the vast emptiness of space, how empty is that actually? Or can we correlate that with absorption signatures that we see? So that's looking at, diffuse gas or median that we're learning because we've studied the galaxies, but only as a tracer of all the big stuff in between. There's a long list of things like this, but it's really exciting work.
It's very cool. And that's where the epidemiology part comes in, because you are studying the path that it's taken and what makes up its path based on the trace elements, which is kind of the thing that you get with genetics as well. And when you do skin cell or hair samples, and you can see where someone was born, the kinds of environments they lived in because of what they ate and the air they breathed, and all of that environmental stuff that you draw into your body as trace elements, the way that celestial bodies and other things like that will collect stuff along the way on their journey. It's all very cool.
It's a beautiful analogy, actually.
Oh, thank you. But yeah, that's awesome. I love that, because you get to learn their story and their path through whatever it is they've been doing through space and time, because all of that is also over large scales of time as well.
It sure is.
So that's your specialty in looking at the galaxies and where they come from as your particular area of research. So what have you discovered so far in particular that has kind of, like, you've already given an example of super shiny things, but what has been something that's super shiny to you?
I like to really, really delve into the details of how we do the processes that we do, which means that the consequence of that is that I learn a lot, but not about the universe, but about how we see the universe, which is not so much in discovery space. So it never sounds quite as exciting when I put it that way. So, for example, one of the things that I spend a lot of time doing is we measure the brightness of galaxies, and then we do that in lots and lots of different wavelengths. And it's usually brighter in the optical than it is in the ultraviolet. And also by the time you move to the infrared, it gets a bit dimmer. And then in the far infrared, it booms in brightness. And that's because galaxies have a lot of dust. So there's all of this beautiful detail in every individual galaxy. But to go from that to, well, this particular galaxy formed all of its stars between 2 and 10 billion years ago exactly. And then it suddenly shut off. And that's how we learn things about the central black hole inside them. To make that sort of link, you need to model this brightness of galaxies. And that modeling process is something that we've made incredible strides in learning about over the last couple of decades. So much so that I think we get pretty confident that we know exactly how we're doing this. And I spent a lot of time digging into those assumptions and techniques and realizing that, oh my goodness, there are still so many things that we actually don't know as well as we do. And we need to nut down into some of these technicalities. We've had a really big reminder in the last couple of years as to why this is so important, because we've had this, spectacular new telescope called the James Webb Space Telescope that suddenly pushed our knowledge of galaxies to the farthest frontier. We are measuring galaxies at higher redshifts than we ever thought we would. And we're applying all of our fantastic modeling techniques to these new galaxies, and we're suddenly getting results that are inconsistent with our understanding of the universe. And we've had news articles all around the world saying dark matter is wrong, or we don't understand the universe, and it can't be 14 billion years old, and, really big, sweeping statements. And a lot of them we can solve just by saying, well, this very basic modeling of a galaxy that we do to get from light to mass has some complexities. and so that's the space that I work in, is saying, okay, well, how do we fix these things so that when we have exciting new discoveries, we have the toolbox ready to make accurate assumptions from it?
Yeah. Well, it's back to what you were saying at the beginning with the models that work for the first few layers and then they just spectacularly fail because suddenly there are enough factors involved that haven't been accounted for yet that push it up. And yeah, when you're working with that volume of data, like, the odds of you not failing at some point, you're just going to have to fail at some point because
completely.
Yeah, there's just too much stuff. And even some of the things that you were working on before, I was looking through your papers and I saw that you'd actually done effectively noise cancellation on the James Webb. Oh, what you called it? It was wisp removal.
That's the one. Yep.
I was looking at it going, you've just edge detected galaxies. How? Because that's just, it's just all of these are specs. Which specs are important? I don't know. And it is talking about how we do the modeling, because there's so many ways to skin a cat. And with maths, you can use multiple ways of coming up with the same answer under very specific conditions. But as soon as you change one of the conditions, one of those formulas will fail.
Mm-hmm.
So you don't know which one of those formulas is the one that's going to be the most resilient over time.
Completely. And the difficulty is that we call this overfitting, in that if you just add more complexity to your model, chances are you can fit your data much better. You can create the answer in a really complex way that looks perfect. But then if you add more data, suddenly your complex model is doing the wrong thing. It's projected it in all the wrong directions. And so it's always that battle between having enough data to support a complex model, but having that model be as simple as possible to not get things wrong. So it's a gloriously sticky situation, actually.
It sounds fun and terrible. So, as part of that kind of work that you're doing, I saw that because it is large volumes of data, you mentioned on your LinkedIn profile that one of the other things that you're interested in is the carbon footprint of astronomy. And I think that is also an equally sticky problem. So, for those who, I guess, are fairly new to this area, when you need a lot of data, well, when you have a lot of data, you need a lot of processing. When you need a lot of processing, you need a lot of compute. A lot of compute costs a lot of energy. And to create the compute, you also need to cool the machines doing the compute to do all that, which is very expensive in terms of power and other sorts of resources, which increases our carbon footprint. So when you think about the immense volumes of data that you're getting at any point in time from any of the data sources in the area of astronomy, that's a ton of carbon footprint. So what have you learned in your analysis of this and the ways in which we can work on reducing the carbon footprint of astronomy?
It's a sticky one, and it's a difficult one because the solution to the carbon footprint problem, the easy solution rather, is exactly the opposite to what we want as astrophysicists, is to delete our data and to do less compute. And that's actually not an option. We won't be doing that because that defeats the purpose of all this exciting stuff that we're doing. So it's about finding the right compromises. As much as possible, it's identifying, as you mentioned earlier, what is the most critical element of the data and restricting the data set to just that. It means we have to be a lot more comfortable with deleting data. And I probably get goosebumps just saying it.
Stress.
Yeah, completely. And I hate it. I had a situation recently where I was working on an analysis product where I started with a 20 gigabyte data file. It was only a couple of thousand galaxies. It was kind of a test bed of the modeling. And by the time I got through all of this modeling and testing and trying it with different configurations, I had on my hard drive 40 terabytes of model output. You know, that going from this small amount to this huge amount of output that I was then having so much fun with, analysis. It's nice for a test bed, but that is an entirely unfeasible mechanism for working on larger scales. And I know I had a conversation with my colleague where he was saying, oh, well, just find that one data product that you need for each and delete everything else. Don't even save it. Just run the outputs and delete. And I thought, but I can't.
What if I need it?
Exactly. And that's something that I need to learn how to do, just like all of my colleagues do. And the reality is that the processing power is big and that comes with its carbon footprint. But what we also forget is that simply data storage has its own carbon footprint, and it's quite a massive one. So in some sense, we're actually better off recomputing things on the fly constantly than we are saving the outputs into one output to quickly query down the line. We live in a world of cloud computing and cloud storage, and we forget that just because the hard drive is not sitting on my desk doesn't mean it's not producing a huge output of carbon somewhere else in the world.
Exactly. And we're able to do things so much more efficiently now than we used to because, before it would be years to process. Like even when I was speaking to a geneticist, they were talking about how one of the projects they were working on took 7 years to do by hand, and with the state of the computers at the time, that can now take maybe a day because we've got the hardware and the power to do it.
Mm-hmm.
So yeah, it's absolutely the trade-off of, well, before we used to have to keep everything because it took forever to generate it to begin with. But now, because we do have the capacity and the technology to be able to do it, we can be a little bit more free with deleting things that we may not need immediately, because overall that's going to be cheaper to delete and not store than it is to pay for the extra compute.
Absolutely. And I mean, the other element of this argument or of this debate is that we need to be better at writing software. And the actual software that we write has to be as efficient as it can be. And I think this is another really strong argument for why it takes more than just a small group of people to do it, science these days, because the real benefits that people have seen in the realm of astrophysics is to actually work really closely with people whose expertise is not astrophysics, but it's software development and computer science. And when you have these marriages of different disciplines to say, well, I know what the software needs to do. And yet astronomers write a lot of code. We do a lot of software development. So it's not something we're awful at. But at the same time, we're not trained to do it efficiently and to do it well and to do it quickly. And so when you have this marriage with someone who has expertise in a different realm, you suddenly get to unlocking massive functionality at much faster speeds and with much lower carbon footprint. So this is wonderful.
Yeah, absolutely. And it's efficiency from the astrophysics side, efficiency from the computing side. And, you're able to also get the benefit of these outside perspectives from people looking at data in a way that's not become their narrow focus for decades. And it allows them to see, well, actually, this is purely a computing or a mathematics problem. I'm not going to look at it as a physics problem. And it just gives you an entirely different view of the way that you can approach a problem, which is very cool as well.
Completely. Yep.
Oh, so shiny. This is why I love talking to astrophysicists, because they do get to work with such a wide variety of people on such a broad range of problems that you don't necessarily see the perspective or the application immediately, but you get this way of being able to get other people's perspectives to contribute to this wider problem that just comes up with this beautiful solution at the end, because they didn't see it coming at the beginning, because that's not what they were looking for at the start. It's all very special and serendipitous.
Serendipitous is one of the beautiful words. Yep.
I'm going to take a bit of a segue right now, because on a rather topical note, there was in the news that the trends in international mathematics and science study, which is, a global testing thing for science and maths, showed that Australia overall improved in their rankings in this area for students between, I think, year 4 to 8, but the gender gap was the worst amongst 58 countries, which I think is very, very sad. Lots of reasons why that might be, but I think it's super sad because we need a lot more people, male and female, in all sorts of intersections in these spaces for the reasons we were just talking about in terms of perspectives and getting skill sets in other areas to be able to contribute to problems.
Absolutely.
So why, because you've mentioned it before, is it so important to have women in the field of astronomy, and what or how does it benefit the industry?
I think a lot of this ends up coming down to the way we do science and not the aims of science itself. And I think we all agree that historically, there have been incredible women throughout history who have made enormous contributions to science. So it's not that it's been a lone field for men, but it's been dominated by men, and the narrative has largely been set by men. And it means that the way we do science is being largely governed by that up until now. The kinds of roles scientists have in terms of what is it that a scientist does at work every day. And I genuinely think that women a lot of the time have perspectives in the workplace that mean the way that we do science is slightly different. Not to say that we, only have soft skills and men have technical skills, but in the realm of skills that we have, I think my experience of female colleagues is that they pay attention to the gaps a little bit more perhaps than the sticky problems that are being solved. We tend to work with people really effectively, and in the realm of really large collaborations and international teams, that is a critical set. And to combine those sorts of outlooks with the technical work that we do is really, really important. I've been in a really big European project at the moment, and it has up to 1,000 people that are preparing busily for a new instrument to be installed in a telescope. And it's still an industry that suffers from having too few women. And I'm regularly in telecons that have 20, 30 people, and I'm often one of maybe 1 or 2 women in the crowd. And it's not surprising to me at all that a lot of the time the people that are quite vocal, or the people that end up finding themselves in leadership roles, are those women in the crowd. And I think that really speaks to the care that is taken and the diverse perspectives that help the crowd that those women can provide. And it breaks my heart a little bit that it hasn't been an industry that has been as welcoming to a broader crowd. You can't be what you can't see. That's not the case for everyone. You get women who don't need to see role models and that can absolutely see themselves in a role, but that's not the case for most. And when you have research groups where there are women in higher positions and you see younger students, both male and female, I don't think this is only for young female students, model their behavior and their expectations differently because of it, I think that's a wonderful thing.
Absolutely. And yeah, as you said, you don't necessarily need to have you can't be what you can't see. I've always felt was very limiting because it's not something that I had really thought about up until it became such a hot button topic. But as a woman of color, which I still find very odd to say, even though it's a technical definition now, I never thought about it that way. I just went, I want to do the thing. I see people doing the thing. That's a thing that I can do. It never occurred to me that gender would play a part or race would play a part in it. But I know there are a lot of people who do very much care about the ratio because they need to see the role models. But at the same time, I don't think you need to see them in your direct line of seniority. You can still find role models outside and in other areas who you can aspire to, who you can seek advice from. And they do not have to be in your specific industry or career to be able to provide you that kind of role model support.
Absolutely.
Yeah. So looking at the field of astronomy and in space as the broader industry, I think it's important for young women who are looking into this area to not worry so much about the ratio, but worry about the values and the culture that they'll be working in. Because if you're with a bunch of people who just care about the goal and who care about the people who they can work with to achieve that goal, the ratio isn't so important.
Yep. I think the one element of this debate where you can't be what you can't see becomes really, really important is, and I actually don't know if there's anything research done on this, but it's a well-quoted anecdote that if you have a job application, for example, if there are 10 criteria, women will tend to expect of themselves they can satisfy all 10 criteria before they will put themselves forward for a role, whereas men are comfortable with fewer. And I've seen this anecdotally around me. And I think what I've noticed when speaking with a lot of junior women as well is saying that I know my value, I know what I can offer, but the skills that I know I can offer haven't been explicitly stated in how I see you doing this or how I've seen you promoting this task, whatever it is, and therefore I'm not the right person for you. And so I see women taking themselves out of the running, not because they're incompetent, but because they think my skill set is better applied elsewhere. And this comment that you make about seeing role models outside of your line of supervision, I think is exactly right, because I can see women and men for that matter, but I think women happen to have some of the skills that I have a little bit more keenly, who've been in various fields, and I've seen them really succeed and do amazing work where I think if we had one of those in my field of research, they would achieve things that I don't currently see. And that in itself makes them an exquisite role model, even if it's not in my direct line. So it's about seeing your skill set and applying it to what you think could be useful as opposed to what you see being directly requested as well.
Absolutely. It's such an important thing because more and more now we're seeing people talking about how selection criteria, it's very prescriptive, but it doesn't consider the intangibles. And people are starting to work that into their applications and work that into the criteria now to talk about how we can identify the intangibles that do contribute that kind of value that aren't specifically related to industry skills.
Mm-hmm.
And yeah, it's a slow change, but it's just making people more aware that these are the kinds of things that we are looking for, not necessarily soft skills, but the ability to be able to, I guess, overcome or think outside the box, all those sorts of expressions that we use to talk about being able to achieve a goal, but not necessarily in the way that everyone else has done.
Exactly right. We've got a very, very strong group here at my workplace that it works phenomenally well together. And it's one of the reasons I would love to stay here for the rest of my career. But the benefit of that is that every new person who's joined the team hasn't had the same skill set, and you build these diverse teams. And sometimes the most difficult thing is to look for something that you don't have. It's because you know what is needed. You know how all these people have been successful. You know how they've managed to make contributions. And so typically that governs how we then hire for the next role. But that's exactly the wrong thing for us to be doing. We should be finding a way to look at everyone's skills for their own merit and see how do they work with what we have. And like you say, we're working on, globally in different industries, how we find that, but hopefully we get better.
Exactly. And I mean, all those additional things that aren't fully in criteria that make each person's contribution unique rubs off on everyone else and everyone grows. And that's how you get even more evolved teams. So yeah, benefits all round.
Absolutely.
So we'll start to wind up now, which I think is a really good way to lead into my last question, which is, what advice would you give someone who would like to do what you do, and what advice should they ignore?
Oh, well, it's hard because I think any advice that I give will be entirely dependent on someone's situation in life and what it is they do and don't do already. Enjoy what you do, but the advice to do something you're passionate about, I actually don't love, because I would say I'm passionate about my work, but I'm passionate about so many things. So my advice would just be pursue passions full stop, but don't expect your work to be fully satisfying your passion all the time, because that's a lie. I love my work, but I don't love everything about my work.
You're a multifaceted being.
Exactly. So be okay with not loving things all the time. If you hate your work or your path all the time, okay, listen to that. But like we said earlier, follow the base curiosity and see where that leads you otherwise. That was a long-winded way of saying, yes, do what you love, but don't expect it to be your full passion. So that's simultaneously advice and advice to ignore. But I think always be open to opportunities around you. Be inquisitive, talk with people. We live in an internet age. I think for any young people now who are inquiring about careers, they inevitably have a lot more information at their fingertips than even I did when I was going through that phase. That I can only imagine is very difficult, because it means you're swamped by information and swamped by advice. And that's a wonderful thing, but it's also an overwhelming thing, and it doesn't help decision making a lot of the time.
You have to learn to be discerning and understanding that you can drop suggestions that just don't apply to you, and that's okay.
Yes, absolutely right. And you can have multiple options that will be fascinating, and that doesn't mean you have to pursue them all either. Just pick one. Sometimes this is my 2025 lesson to self, is don't say yes to everything and don't pursue everything that you'd like to do, because it degrades the quality of the things you do end up doing. Find nuggets, follow them, and as much as possible, think of yourself and be happy while you're doing it.
Oh, that's good advice, and applies to all areas of life.
Easier said than done, but it's a thing to achieve.
It's a general philosophy.
Absolutely.
Very cool. Well, thank you so much, Sabine, for speaking with me today about your journey and your work. I've really enjoyed nerding out with you about astrophysics and all the cool stuff that you're doing on the scale that you are doing it. So if people would like to know more about this area, where can they look?
Well, I do have a website online, so if anyone's curious, there are a whole bunch of contact details there. Do feel free to reach out. And at least where we're based in Perth in Western Australia, we've got a flourishing hub of astronomers that are building across a broad range of spaces, based at the International Centre for Radio Astronomy Research. Look us up online and you'll be privy to the broad range of activities that we do here.
Absolutely. ICRAR, ICRA. It's very, very cool. Lots of activities and events that you guys do run. So if people would like to know more about that, they can go check those out. And I'll also put links to Gamma Waves and Devils, another project that you're involved with, up on the website as well in the show notes.
Please do. It was wonderful chatting with you this morning, Michelle.
Yes, absolutely wonderful speaking with you today, and I hope you have an amazing rest of your day.
Likewise to you.
If you enjoyed this conversation, please let me know. Subscribe to this show, leave us a rating, and share this with your geeky or geek-curious friends. You can also support Steam Powered on Patreon and the Steam Powered Show, the link for which will also be in the show notes. Thanks for tuning in, and we'll see you next time.